everyone. Welcome everyone to day 3 of Understanding Latency 3.0. I'm just finding the agenda. I forgot to put it up. So just give me 2 seconds. We've had a couple of excellent days. And we have another very good list of presenters and topics for you today as well. Just give me 1 second and I will put up the actual agenda here. There we go. So this is the agenda for today. First, this is the introduction. Then Shizong Geng from Huawei will talk about measurement methods of a Cloud Network Experience Index, which is a way of translating latency measurements into application scores. And then Matan from Samsung Research will talk about enhancing real-time traffic latency in Wi-Fi networks from the smartphone perspective. Then Dean will talk about latency and networks in the real world. Mayur from Vodafone will talk about redefining latency testing using app outcomes to measure impact in lab environments. Then we'll have a short break before James Carroll from Ookla talks about Internet of Observability at the global scale. And finally, Koen de Schepper from Nokia Bell Labs will talk about L4S on Wi-Fi. And just a reminder about the practical details. So we will be recording the event, and the recordings will be put on YouTube as soon as we are able to manage that after the event is completed. And once they're live, we will send everyone who signed up for the event an email with the links, and we will update the website with direct links to each of the talks. So everything should be very easy to find. We will also publish the slides, and those will also be sent, or links to those will also be sent out in that same email. So I think it should be easy to find. And yeah, I think that's everything for the introduction, actually. So, Jason, if you are ready to present, you can share your screen. Jason Geng is the Chief Research Engineer at Huawei. We're talking about the Cloud Network Experience Index. I will stop sharing so you can.
Okay. It seems like the video doesn't work. Can you see me?
I cannot see you, no. I can hear you though.
Okay, maybe this time.
Yes, there we go. Perfect.
Great. I will share my screen. Okay, can you see my screen?
Yes, I see.
Okay.
I see the PowerPoint sort of not in presenter, or I don't see the presentation. I see the whole PowerPoint screen.
Okay, how about this time?
No, same thing.
Same thing. Actually, I'm already presenting it. I will try again. Maybe I can share the whole screen. How about this time?
Yes, now it's working. Perfect.
Okay, great. Thanks, Bjorn, for inviting me to give this presentation. And this is Xuesong. Today, I will introduce our work about the measurement method of Cloud Network Experience Index, representing other members in our team, Sifa and Yaojing. This is very important for cloud vendors to monitor the network performance. It can be used to track the customer experience and to provide better cloud service. In a typical cloud accessing scenario, the network could be divided into three segments. The first one is the intra-cloud network, which is from the VM to the POP, and the second part is the internet from the POP to the edge of the carrier network, and also the last mile in the carrier network. So the internet part has the widest coverage in the entire process with the quite high network complexity. So the quality of public network has a great impact on the cloud applications, while it is difficult for cloud vendors to directly access the application level key quality indexed data, which is KQI. So with this as the background, we would like to propose a method of evaluation network quality for cloud applications. The intuition here is to derive customer experience from the basic network metrics for facilitating network optimization. And our goal is to have a unified evaluation method. But there are several challenges mainly come from two aspects. The first one is cloud vendors and the cloud enterprise use different network indicators. As different KPI in order to anticipate the quality of customer experience regarding various applications like gaming, audio, video, online stores. However, KPIs only provide some information. It cannot directly reflect the customer's experience. On the other hand, there is no unified evaluation method for experience quality in the industry now. It is difficult for cloud vendors to directly access application level KQI, though it can describe the customer experience very directly. So we propose an index which is called CEI. It is short for Cloud Network Experience Index. In CEI method, we use a comprehensive formula which could incorporate most important network performance metrics like latency, packet loss, and jitter. Actually, we have made some important choices when we design the method of CEI. The first choice is that we use continuous function rather than discontinuous functions, considering that a continuous function has better analytical property. It can optimize the parameters while the requirement changes. And the second choice is that we use sigmoid function to model the relationship between network metrics and the user experience. Sigmoid function is an S-curve. It is a normalized function. We can use it to align with the three-stage characteristics of user experience. It means like below a certain threshold, user experience is not sensitive to changes of network metrics. And within a certain range in the middle, the user experience has an almost linear change with the growth of metric value. And above a certain threshold, user experience has already degraded so significant. So, and doesn't change further with the increase of metric value. This is showed in the figure as two smoothing zones and one sensitive zone in the figure. Also, we have the third choice is that we have introduced. Oh, it seems like there is some noise from my side.
Yes, Nina, can you mute the other
Yeah.
connection with the same with Shezong's name? Thank you.
Okay. And And we have third choice. The third choice is that we have introduced two parameters to make the function fit into different cases. Parameter A represents the overall slope of the curve, mainly affecting the range of the central sensitive area. And the parameter B represents the offset and the scaling of the curve. The initial smoothing area can be shielded via tuning B, which can express KPIs that immediately enter the sensitive area from the very beginning. Also, we have introduced three dimensions for CEI, including latency, packet loss, and jitter. It is the weighted sum of three sigmoid functions. The weights represent the importance of a specific metric in the user experience evaluation. And different applications can use different weight values to reflect the impact of various network parameters on the experience of the application. It means that like the CEI has the flexibility to allow for fine tuning to meet specific application requirements by adjusting its weight values. So in order to determine the proper value of the parameters I have just introduced, like parameter A and parameter B, we have designed a parameter learning process with pairwise learning method. We collect a set of data, including the value of network metrics and the CI results. The data comes from two sources. One is user complaint data that describes the customer experience, and also from the expert preference. We randomly generate data that matches these descriptions. And with this data and the learning process, we finally get the following parameters for three network metrics. And here I will give an example. We can use the CEI method to evaluate the quality of service for a typical latency sensitive cloud application. As mentioned earlier, the CEI function itself consists of three sigmoid functions, each representing a network metric. As shown in the table, we assign weights of 70, 20, and 10 to latency, packet loss, and jitter respectively. At the same time, we use the collected data to determine the values of the parameters A and B in each sigmoid functions for each metric. Then we plot the CEI figure for latency, for packet loss, and similarly the jitter CEI curve, but it is omitted here. Taking latency as an example, we can score the cloud service using the CEI value by measuring the latency of the network from a single carrier to a cloud vendor. Similarly, we can also measure the latency of the network from multiple carrier to a cloud vendor, score with the CEI, and then take the average value. We can set standards for the CEI values to differentiate the performance, like excellent, good, and poor performance. The following figure lists some examples used to evaluate service quality of Cloud A and Cloud B. We then attempt to use this method to evaluate the cloud service quality across different regions. This image is a screenshot from our current internal website, which uses colors to displays the CEI scoring systems and ranks the regions. For selected cloud services, it can show the proportion of network quality over a certain period. It also allows the option to display CEI results for different metrics or to choose the comprehensive results. We can also display this as a table. If you use days as the unit, it shows the CEI values for each day and the trend of the changes over a period of time. it can be seen that the CI method can enable the cloud vendors to proactively enhance network services, and it can be used for network planning, construction, and so on. Furthermore, we think it can enable cloud customers to distinguish the service quality of various cloud vendors, allowing them to select the most cost-effective service tailored to their own applications. That is all from my side. Any questions to our work?
Thank you very much, Jason. There are a
Mhm.
few questions in the chat actually. First,
Yeah.
Flavio is asking, are there any references for us to read on this? I couldn't find it on Google, so I hope you can send the link in the chat to the internet draft.
Yeah, okay. We have an IETF document to describe this work. I will send the link to the chat box.
Very good, thank you. And then Kelvin is asking, this sigmoid function has pre-selected thresholds that correlate with the game experience. Does this imply that there would have to be separate CEI calculations for different use case types that have different latency targets?
Actually, the if you see the example here, the in the table, the weight here is how we feed this function to different type of applications, because different type of applications have different types of sensitivity to these three metrics. So by tuning these three weights value, we feed this function to different applications. Also, we can tune in parameter A and parameter B, but it depends on the type of the applications and the requirement of the customer.
Right.
Mhm.
And then Madhan is asking, a lot of real-time gaming uses UDP, and he's asking how this index can be generated for that use case. How can we fetch latency, packet loss, and jitter for UDP traffic?
Actually, in our test, we have two methods of measurement. The first one is proactive measurement. We have some cooperations with service providers. So there is a server in service provider. We can send a packet from the server in the cloud to the server in the service provider to measure these metrics. And the other way is passive measurement. There can be some app in the end user, and we can just measure the latency, packet loss, and jitter between the end user and the server in the cloud. So both can work here.
All right, perfect. Thank you very much.
Great.
With that, we'll move to our next speaker for today. Our next speaker is Madhan Raj Kanagarathinam. Kanagarathinam. Sorry, Madhan. I'm trying my best here. He's a software architect in the connectivity R&D department at Samsung Research India, and he will be talking about enhancing the real-time traffic latency in Wi-Fi networks from the smartphone phone perspective. We can both see, hear, and hear you, and now I can see your screen as well.
Okay. Yeah. Thank you. Hello, everyone. So today I'm going to tell the story about enhancing the real-time traffic latency. So we have seen lots of perspective from the network, from the RAN, from the core, and so on. So I'm going to focus only on the smartphone or the station or the user equipment UE. So this is a well-known story. Like post during and post COVID, we saw a huge spike in the real time applications like video calls for the office works, and we have the webinar now, and we also have seen a surge or like it the online gaming also skyrocketed. So we saw 3x the traffic post, and even during and post pandemic, we saw more traffic. And these online mobile gaming and video conferences, they need low latency and very minimal packet losses to ensure smooth and immersive experience. This is not like the web browsing or download, which has more requirement for the throughput or the latency. So a day-to-day scenario. Let's consider like we have a Wi-Fi in our home, and let's say your phone is connected and you're watching something live, let's say live streaming or a live video. So then there will be multiple devices connected, and it can run different types of application. Someone can be downloading, someone can be playing game when you're on the Zoom call now. So this is a very common scenario. So once the link is getting saturated, what we see is sometimes the real-time traffic is affected. So we see buffering in the video. The video might get spotty, or there might be some pixelations and so on. So due to so we are going to see what we can do only from the smartphone view. First, sorry. In case of Android, we have this auto download policies. We have some background download going on where the traffic can race in the same device. So when you're doing a video call, there can be a Play Store update going on, or someone might be sending you a video, or you might download a large file. So there could be a race between the best effort traffic and the real-time traffic. So what we observed was during this scenario, the video can be spotty, and the online gaming there was huge spikes and also few jitters. So since the traffic is in same device, can we control the downlink traffic? Was the question. So yes, we can control. So how we can control is the next question. So can we delay or drop or shape the packets, or we can play around with the advertised window instead of dropping the download packets or delaying the download packets. So these were the possible options in the literature, and yes, we try to use this. So this is part of the intelligent Wi-Fi setting. So if you're using a S24 or S23, you can see this in the phone. So where we try to, if you have a download in the background, and if you have a video call or game in your foreground, so we automatically try to prioritize the gaming by controlling the background traffic using any of the shaping technique. So the advantage is like it does not depend on any server or middle boxes, and it can be app agnostic as well. But the disadvantage is like it's not very common scenario, right? So not all users are going to download when you're in a Zoom call on the phone, and there is also specific scenarios where there can be someone else connected to your Wi-Fi and is trying to saturate the traffic. So yeah. So next, what we thought was like, can we use the help of the access point as well to certain extent? So this is the story of station plus access point working together. The common challenge faced by the smartphone users when we are connected to the Wi-Fi is the inconsistency in the QoS among the different applications. So Wi-Fi provides certain QoS management techniques. We have SES, which is the stream classification service. We have MSES, where we mirror the stream classification service, and we also have the DSCP mapping. So today I'm going to touch upon the DSCP mapping mainly. So where we're going to talk about the DSCP and the access category. So we have like four well-defined access categories. So we have voice, video, best effort, and the background. And we also have a well-defined RFC 83225, which talks about which DSCP has to be mapped to the specific user priority in the 802.11 Wi-Fi standards. So just for the information along this table, so what we'll be seeing today mostly is like the real-time video and the gaming. So which is to be mapped to CS4 and should be in the VA access category. Next, the question: how many like we tested the top chart gaming apps and also the video calling apps to check what are the DSCP values which is being set, or what is the actual access category or the priority being set in the Wi-Fi uplink and the downlink. So we saw a lot of presentation in the first 2 days where we found like DSCP is not properly used, or it's not it's mostly 0x00. So yes, that was the result. So I even conducted some experiments like just before a couple of days to ensure this problem exists. So yeah, so when I tested with PUBG Mobile, Call of Duty, Free Fire, Clash of, I mean, these are from different SDKs, gaming SDKs, and different gaming companies as well. And even I tested Meet, Teams, Zoom, and WebEx. So what I observed was most of them were using DSCP as zero. So mapping it to the access category as zero as well. So when it's like the downlink packet, so definitely there can be an impact because of the middle boxes. There can be it can be bleached even if server is trying to send something, or there can be some firewalls which can modify the packets. So the downlink can vary. So sometimes I saw 0x20, which is background, and sometimes I saw 0x00. Most of the times I saw 0x00 in different networks in different regions. So this is the problem, right? So what we have is like most of the real-time gaming and also the video traffic. I mean, I didn't find this problem in the audio traffic for certain reasons, but most of the video traffic and the gaming traffic is in the BEQ, so which has a different contention window. So what we want to do is like, can we move this into the VIQ? So that's the challenge. So as I was suggesting, so we have this Q box, which is in all the Samsung devices. So the aim is like whenever we know like there's a video call going on, or when there's a real-time mobile game you're playing, when you're playing your PUBG Mobile, for example. So can you, if it's like best effort, can you upgrade it to video? Or let's say there is some other app which is trying to misuse the video or voice priority. Can you downgrade it to the best effort? So to appropriately match the priorities is something which we aim for. So what is required? So first step is like to classify the real-time traffic. So what we do is in Android, we can get the context. So we can know like a video call is going on, or like streaming is going on, or we can also know about the foreground activity, which app is running, which app is not running. So just knowing by app, you cannot differentiate the traffic, right? So for example, now we are in the Zoom call. There can be, I mean, someone can be asking some questions in the chat, which has to be treated differently. And I'm talking, the voice has to be treated differently. And there's a video sharing as well, which has to be treated differently. So we need this final classification, or at least we need like classification of real time and non-real time. So using the eBPF attached to the Wi-Fi interface, we are extracting the packet characteristics. So rather than a DPA or a DNS or any other method, so we are going to observe the packet characteristics for the certain interested apps, and we are going to further extract the sessions which can be mapped as real time and non-real time. So now we have the list of interested sessions. So we have the BPF map, which gives the cookies or the session keys, which are to be upgraded to video, for example. So we know which app we have to see, and we also know which connection we have to see. And in the egress, we try to upgrade or downgrade the DSCP value. And in the driver, we try to upgrade the access category as well. So what we do now is like if you're doing a Zoom call, let's say in your Samsung device. So even if the Zoom sets 0x00, we upgrade it to CS4, and the uplink traffic is upgraded to video. So I mean, we observed like very good accuracy in the detection, and we didn't classify anything wrongly. That's a good thing. But we missed few packets due to the initial training phase. But nevertheless, most of the time we were able to classify the video packets, video streams correctly. And as I was asking my previous question, so if it's TCP, we can kind of get the parameters. We can use TCP info, or we can even use BPF timestamps and so on to get the TCP parameters. So how do we get for the real-time gaming? So real time, again, we have two categories. So video calling and gaming. So video calling, somehow we found like the bitrate or the RTP is highly correlated to the QoE. But gaming, there was no correlation between the video calling app, sorry, the bitrate and the QoE. So we found a very low correlation. And what what we observed was like during the gaming, there is assistant TCP connection. So I was trying to tap the RTT stats and packet loss of this specific assisted TCP connection. So it had some correlation, but was not highly correlated. So I was using I mean most of the games. This is the PUBG game, so on the real time. So it used even the Call of Duty and most of the games, they used to display the one-way latency here or near the map or somewhere in the screen for the gaming purpose. So I was using a OCR to extract the latency and just for the evaluation purpose. So what was observed was like so I built again two scenarios. So I had a middle box. I fixed a box which just replicates the TOS values. So when I set 0x80, the middle box sends the downstream also with 0x80, something like that. So when I'm able to modify the access category or the mapping of both uplink and downlink, so I was seeing a very good impact. So there was like up to 20-24% improvement in a saturated network condition. And when it was just the uplink, I saw up to 10%, 5 to 10%. So there was not much benefit, but it was a pretty decent end-to-end latency improvement. So summarizing my slides, so what we have in 3.0, what we discussed till now is the star-only app agnostic solution with partial AP support. So the wish list is to have like full access point support where we can use SES, MSES configured properly and proper scheduling mechanisms. And also we can use the multi-link operation in Wi-Fi 7. And the major or the main wish list is like to have the end-to-end latency support, like what we have in L4S or the application server RAN, everything talking to each other. So yeah, that's it. Thank you, everyone. I can see there's a lots of questions.
Thank you very much. Yes, there are many questions. Let's start with Jason is asking, how can we learn more about Qbox?
Okay. So I have added the reference of everything. Like I have added the reference of Qbox, and I have added the reference of how do we extract the latency, and even the settings which is enabled. So I'll just drop in the chat box as well. Thank you.
All right. Thank you. And Saidiraj is asking, how do you get measurements back to network if it's running on a phone? I'm not entirely sure I understand the question.
So this is an on-device measurement and on-device algorithm. So we no need to send it back to the network. So everything is on-device.
All right. And Usman is asking, how much battery load does this inference cause on the handset?
The eBPF, so the beauty of this algorithm is like we are going to do it like event driven. So only when there is certain applications which is going to run, we're going to inspect those packets. And since it's event driven, so we didn't find much of the battery or power usage. And eBPF being lightweight, so the processing and the CPU utilization was also less than 0.01, I think. Yeah.
All right. There are a few more questions, but I think we will move to the next
I'll take it
speaker.
over
So
the chat.
yes, if you have time for that, that would be excellent. Thank you very much.
Thank you. Thank you. Thank you, everyone.
All right. Our next speaker is Dean Bubley with the disruptive analysis, and he will be talking about latency and networks in the real world. So Dean, please take the stage.
Thank you, Bjorn. Let me see if I can get this to share. That should be up now.
It is, yes, and I can hear you loud and clear.
Fantastic. Right. So my presentation's a little bit different. I'm not a researcher or an engineer. I'm an industry analyst and advisor. And so, I'm going to give a little bit of context on what I'm seeing with wireless networks and trends in, well, also fixed networks to a degree, but also what's going on in the larger world of connectivity, the business models from different service providers, and enterprises, and what that means in terms of the network context for latency. And to be honest, it speaks a lot to the need for things like L4S, or what I'll call intelligent adaptivity or informed adaptivity of applications, because the network itself is likely to be unpredictable. And unfortunately, the nature of network deployments and operation means that unpredictability and variability is probably going to increase in the future in general, although in some specific situations, it may be more deterministic and a bit more straightforward. So the key for me is that there's a lot of questions about where the end user is and what they're doing and what network or networks it's connected to, which ultimately then drives what is deliverable in terms of latency. And I started thinking about this a long time ago, but particularly recently, there's been a lot of discussion around a concept called quality on demand, which also aligns with quality of experience, quality of service. And I know Dom works on quality of outcome as well. Quality on demand is a term often used in on demand is often used in the wireless industry, where the theory is that the device or the application or the user can request some sort of performance guarantee from typically a mobile network, but also perhaps a fixed broadband network and Wi-Fi. The idea for the industry is that they should be able to charge people for this enhancement, whether that's guaranteed uplink or downlink throughputs, or potentially banded latency for certain applications as well. My general view is that that is very hard to do, except in some specific circumstances, and I'll talk through why that is. And I think firstly, the question is about where the device and user is. Are they indoors? Are they outdoors? We'll talk about that in more depth in a second. Static or moving. Clearly, if you're on a car driving down a highway, then you will be moving from one cell to the next, or the vehicle will be. And so therefore, trying to guarantee consistency and latency is very hard, because each cell has different levels of load and congestion and where the towers are and so on. What networks or possibly network plural is the thing attached to, who owns and controls it, and do you have insight or control over what they're doing? I've got a couple of slides on server and edge computing, because there's a lot of discussion at the moment around edge computing, and whether putting an edge server in the network, and I'm thinking particularly a lot of the recent noises around putting an AI-capable box for radio network optimization or control in the network, and operators and some of the vendors are asking, can you sell spare capacity on that server, whether it's GPUs or CPUs, and offer that for low latency edge inferencing or other edge workloads? And again, that's not as simple as it sounds. I've got a slide I had from a few years ago, which is a sort of hypothetical one on value of latency, and I think it might be a good discussion point, and a couple of musings about AI. So I'll come back to this idea of informed adaptivity, and the more information the network can give to the application to optimize its own latency characteristics and delay and queuing, use of differential queues or L4S or whatever, the better. So the dirty secret here is, unless you've got good connectivity, which especially in wireless means network coverage of high quality and with suitable spectrum allowance and essentially configuration, and in some cases regulatory rules as well, in terms of how that wireless network or spectrum band is allowed to be used, your chances of being able to deliver low latency, especially the sort of millisecond latency promised by 5G, diminish. And a key one that I spend a lot of time thinking about is the indoor versus outdoor split. And there's an important point here is that for wireless networks, the higher the frequency of the radio, the worse it is at going through walls and windows. Um, and what that tends to mean is that you use lower frequencies for indoor users, or you need to have some sort of indoor system, whether it's a repeater or what's called a distributed antenna system, or you use Wi-Fi instead, or perhaps even a fixed connection. Whereas outdoors, you've got a whole range of different spectrum. You can bond them together. You can have a certain amount that's reserved for low latency users or high priority users. That's often not the case indoors. And I think that that does not get enough attention because often, particularly if you're using a cell phone indoors on the radio network or the wireless network rather than on Wi-Fi, you may well find that it's constrained or you may have no coverage at all. And when I say indoors, it's also worth thinking there's lots of different contexts here. So I'm not going to go through this now, but it could be residential, it could be a commercial space like a shopping mall or an airport, it could be industrial like a factory, it could be transport. So yeah, you could sort of classify trains or buses as an indoor environment where you've got all sorts of factors in play. Again, moving around, high density of users concurrently, complexity because of, in some cases, the windows have a lot of shielding in them and so on. And so what this means is that from an application point of view, unless you know where an endpoint is and what it's doing, it's very difficult to characterize the network and its performance expectations. And even simple things like changing over type of glass in the window, and particularly if it's structural glass, which is an entire wall, have massive implications on the connectivity. So this is just an example where I was sitting right by the window in a new part of London in King's Cross. As you can see, 2 meters from the window, and I had no signal at all. Simply because essentially the foil in the window for insulation purposes blocks out certain frequencies of wireless, and that's going to get worse as we get better insulated buildings, whether it's windows or walls, over the next 10 years or so, with moves to more sustainable construction as well, because the construction industry is more interested in the thermal characteristics than the wireless ones. So again, this has impact not just on latency, which essentially it's for throughput or any connectivity. And what you may well find that is if you do get a signal, it's so weak that you're getting so many packet retransmits that the latency is horrendous. So where does network connectivity, where is it predictable enough to guarantee low latency? On a cellular network, I would say the first thing is you're starting to see emergence of private networks, 4G and 5G, mostly in industrial sites. It could be mines, factories, warehouses, ports and airports, and some other locations as well, where they've actually been engineered for specific applications, got enough capacity, the small cells or outdoor cells positioned. There may be redundancy, so a given robot or vehicle can see two or more of them, and so there you've got a much better chance of engineering the local network for low latency performance. Similar situation in certain venues where, again, there's been a real effort that's been made around dedicating the coverage to, it could be even a one-off event like a Formula One Grand Prix, where they will know that they need extra capacity at turn 3 or on some of the stands, so they'll bring in a temporary cell tower for additional capacity and coverage. And then in some metro areas, you will find, particularly outdoors, where there's, again, enough spectrum, there's a lot of good design, where the city authority is quite favorable to siting of antennas on roofs or walls or lampposts or whatever. Then you may well find increasingly there's reliable networks there, which is the baseline for low latency capability, even if the 5G promise of 1 millisecond was vastly overhyped. The other complexity here is public networks are just part of the wireless landscape. I already mentioned Wi-Fi, private networks. You have to think about other things in the future where you may find devices that are connected to multiple devices, multiple networks simultaneously, where you have satellite coming into play, which can be very good for coverage in rural and remote areas, but obviously is going to add latency in some cases, depending whether it's low Earth or geosynchronous orbits, and it may well go via a gateway or an Earth station, which is some distance away as well. So there's all sorts of sort of complexities to consider here. So what I'll say is that what this means is that networks increasingly will have boundaries. So whether it's your device connecting to two networks or more simultaneously, cellular and Wi-Fi is a good example, or where you've got essentially boundaries inside the network, where you may well have, firstly, you may well have firewalls or border controllers of one form or another, but you've also got different commercial relationships between the parties. So you might find a split between wholesale and retail providers, where on a fiber side of it, you might find there's an open access fiber where the optical layer is run by a wholesale operator, but then the retail ISPs handle the IP layer on top of that. In mobile, there's mobile operators and what are called mobile virtual operators, which are quite common in a number of countries around the world, where there's a wholesale relationship. Even within MVNOs, some of them have their own core networks, some of them rely on their host network core, so there's differences there. Various other models around shared infrastructure in future as well. You'll also find that coverage in some areas is extended, perhaps via a third party. So there might be a dedicated provider for indoor use, for industrial sites. I mentioned satellite. There might be a shared network run by government for a rural or remote area. And so at those boundaries, how you manage latency, which crosses multiple domains, or how you measure it, is a hard problem, because it's not like there's one template for this. And you also will find increasing numbers of situations where connectivity is what are called daisy chain. You've got one connection, then another, then another. So it might well be, your phone connects, or your headphones connect via Bluetooth to the phone connects via Wi-Fi to a router, the router uses 5G fixed wireless access back to the network. And trying to manage a latency budget across all of those separate sectors which are independently controlled could be an interesting challenge. Wi-Fi mesh may bring in additional challenges, use of VPNs and so on. So the key thing to think here is that the network environment is getting much more complicated over time. Right, I'm going to switch gears quickly and talk about edge computing, and for years I've used this slide for about 6 years, or variations of it. And the question is, where is the edge? And actually, what's happened over the last year is the edge is where the energy is. And so what you're increasingly going to find is compute resources not positioned for theoretical optimum latency, but for access to large amounts of power. There's an awful lot of the cloud companies that have this year announced nuclear strategies, building out in future maybe small modular reactors, or building new data centers next door to an existing plant. You're also finding interest in end devices where the power for a home gateway comes from the wall. It's not battery powered. And actually, a lot of the discussion around edge computing, whether it's the old-fashioned what was called MEC in the sort of 5G era, or AI RAN for the current fad around AI servers for Open RAN and a few other things, other network edge and micro data centers. To be honest, you can think of this as a barbell or a dumbbell, where the main compute is going to either be on the edge device collectively or in big data centers. The bit in the middle is problematic for all sorts of reasons, as well as energy. Often it's not very well interconnected with the rest of the internet, which has, again, latency implications there. This chart I did a few years ago, and it's not based on hard numbers, but I think one of the things we don't discuss when we talk about latency is, where is the value in low latency? Is it about better gaming performance, better industrial automation, and what are the cohorts of latency that matter in terms of the application? So a lot of discussion we talk about is in this sort of 1 to 10 millisecond bracket, or 10 to 100. But I thought more generally about the overall space of sort of connected devices and users and applications. I've spoken to people who are talking about femtoseconds or nanoseconds for laser etching of surfaces, for example, right up to people in the IoT world who are fine with the measurement being taken once a day, once a week, or even once a month. And I think that there's no good real idea of, when we look at the value of connectivity, how that breaks down into these different sort of cohorts. And here I've got, like, I think it's 12 orders of magnitude on this slide in terms of latency. And where is the money from the service provider point of view, the cloud provider point of view, the user? I don't think it's all concentrated in this 1 to 100 millisecond, two bins there, but in some of the ones that stretch out on either side of that as well. So that's not a hard set of data here. It is me putting some just finger in the air estimates, but I've not seen anyone try to break down where is the value by latency cohort. Last one, part one, and I realize I'm low on time. In 6G, you'll often see this diagram advanced by the ITU. I've annotated it with these coloured add-ons. And there's this term hyper reliable and low latency communications, which follows on from the 5G promise of URLLC or ultra reliable. We're going from ultra to hyper, according to the ITU framework, which is aiming to get 0.1 millisecond latency out of the next generation of wireless networks. I am skeptical that is either valuable or deliverable or an efficient use of wireless resources. And it's very notable that in a recent document I saw from one of the other industry bodies, that they switched from hyper to high, which actually were all reliable. And actually they focus more on the reliable latency rather than the shortest possible. Might be something we see a pivot to over coming years. And the very last point, and this is something that I've been wondering for a while, is can we use some general Gen AI magic to hide over latency or other network issues? Increasingly, you're able to sort of generate stuff almost on the fly and on the device, such that if I, for example, this voice call suddenly drop out for half a second, in theory, I could allow a Gen AI application to fill in the gaps for me, so if you like, sort of varnish over the glitch. I don't think we're there yet, but it's something that I think that we should perhaps watch out for. The diagram there, I was pondering whether maybe in future, rather than streaming gigabytes of video, we simply ask Gen AI on our TV to say, I want to see a James Bond movie where he jumps off a cliff into a hovercraft and gets chased by killer drones. And you've got 100 bytes rather than 4 gigabytes of streaming, and it's just generated locally. So on that, I'll pass it back.
Thank you very much, Dean. In defense of the 6G researchers, you have to get the research funding somehow. Right?
Yeah, I mean, the thing I noted there was this thing 6G reset, which myself and a speaker on day one, William Webb, and another colleague of ours is running, which is almost like trying to think, well, how do we make 6G useful for the real world, rather than something which is academically pushing the spider diagram to all the vertices even further.
Indeed. There are a few questions, I think, but we are a bit over time. So I think if you can address those in the chat, that would be great. And thank you very much. Our next speaker is Mayur Chanagauda from Vodafone. He's a technology architect within Vodafone's Fixed Access Center of Excellence team, and he'll be talking about redefining latency testing using application outcomes to measure real-world impact in lab environments. So Mayur, the stage is yours.
Thank you, Bjorn. I hope you can hear me and see the screens.
Yes, I can.
Yes, just continuing on how Dean presented it. My presentation is a bit different to the different presentations in the last 2 days. My name is Mayur Chanagauda. I'm a broadband architect at Fixed Access Center of Excellence in Vodafone. I'm going to talk to you about what we are doing in the lab, how we are changing, how we collect results and look at tests. Just a bit of background, we are a bit lucky team. We get to play with new fun technologies. So in recent years, we are looking at latency improvement technologies, predominantly at the home and access networks. We're looking at the technologies such as WMM, low latency APIs from chipset vendors, Wi-Fi 7, MLO, and other things. We're looking at the access network as well, low latency DOCSIS, different AQM techniques, different types of PON scheduling, and also virtualization as well. So looking at impact of virtualized network functions. Last but not the least, L4S as well. So typically what we do in the team is we get interested in a technology, we do some research, we run some lab trials, and if it's promising, we go to the next stage, which is run some field trials. And usually our field trial results looks like the graph I show there. So it's a technology improvement for 20 trialists. So we draw some really nice CDFs of before and after, where we show them what happened, how was their latency before, and how did the technology improve by showing some percentiles. And then if we see a good improvement with the technology, then we go to our commercial teams, and then our commercial teams are very uh, uh, funny guys. They ask the good questions, which is, yes, you did improve the latency and it was great, but what does it mean to the customer? Did the customer actually see their QoE getting better? If so, what application categories? And even if it didn't, most often it's very difficult to see the QoE from the customer point of view. So then they ask you even tougher questions. How much does it cost? And can we only do it should we do it for everybody or just a few of them? What kind of access customers would see the most benefit? So what we typically do again is runs few more lab tests and change our field trials, and this is becoming really expensive for us. So what we want to do as part of our lab test is and also to focus a bit more on the field trials is to look at more on the application QoE impact from the customer point of view. So not just showing CDFs, but also to show how better the QoE for different applications got affected with the technology. It has other effects as well. So we really want to know how to assess customer impact a bit more. So we want to spend a bit more time on that. And also it helps us for targeted technology investments. So improving end-to-end QoE is not just one technology, it's a set of technologies coming together. So how do we do it? What phases do we do it? So those kinds of commercial questions as well. So in order to do this, we're investing in two things in the lab. One is to investigate end user impact. So we're along with your beautiful CDFs of latency, we also want to bring application QoE as well. So let's say you have your greatest Wi-Fi 7 MLO improvement from Wi-Fi 6. What does it mean to, let's say, video streaming applications? So what did it change there? So what did it change for video conferencing or gaming? So we want to look at the QoE metrics, timeliness, temporal and spatial aspects, use different QoE models, and look at from an end-to-end point of view how each application is getting affected by the technology. So that's one piece. The second piece is we want to use the data that we already have. So we have run some field trials. We have probes in the networks, and then we have some basic data about how our networks look like. So we want to use that data. So for example, we want to create latency profiles based on customer types. So what kind of access network they use? How does their home look like? How many Wi-Fi extenders do they have? So what are the neighboring APs like? And if we have probes in their homes, then we get the latency measurements for wired and wireless. So we get a pretty big picture. So what we want to do is to build different latency profiles, merge it with the application QoE outcomes, and see which customer gets the most benefit. Where is this technology making a bigger improvement? So this is how our lab now looks like. So along with running your traffic emulations, looking at your TVAM tracers and other things, we are investing in applications. So we're working with application developers, open source communities, where we're looking at the different ways to collect QoE metrics, referencing standards where we have some QoE models. I'll talk a bit more about that. And then at the end, what we want to say is with this technology for this particular latency profile, where you had different kinds of congestion and the customer type was this, live streaming was great. or short form video was great, or maybe cloud gaming was really bad. So it didn't provide so much improvement for them. And then these answers with the experiments are quite useful. Then we go back to our field trials. So in the first instance, we know whom to target. Second, we know what's the benefit of doing this, or should we do it now, or should we do later? So these kind of results we could answer by learning such trials in the lab. We are not alone in this. I think if some of you guys have attended previous Domos webinars, there was an activity called the TIPA MRN QoE QoS relationship. So that's one activity we participated in, and it exactly looked at the problem we are facing in our filters, which is to look at the QoE and QoS relationship. As part of that activity, the group looked at what are the different QoE metrics, how they affect QoE for different application categories. They looked predominantly at SFV, your TikToks, videos, and other things, and also for AR, VR, 3D volumetric applications. They also defined the QoS relationship as well, and they had a comprehensive list of QoE models that could be employed, and also some measurement techniques that could be used. So we leveraged some of those work. So I put some examples here, but there's a link there where you can go check it out. So we got lots of references from there. So that's some of the models that we are using in the lab as well, where we are as part of the experiment, we are also looking at the QoE metrics for each application categories. I thought instead of talking, let me show you some of the results as well. It's very basic. The first screen that you're looking at is along with it's an experiment where we are looking at. I think this was for different values of delay, jitter, loss, and burst. And we ran our typical latency experiments. But what we did as part of that experiment was to run video on demand, low latency streaming, ultra low latency streaming, and 4K. The green chart shows you the MOS score that was derived from the QoE model mentioned above. So it's from 0 to 5, and also we looked at the upload and download ratios. It looks pretty basic, but it gave us one important information, which was what's the upload and download ratios for different streaming types. It helps us in our capacity planning. That was really neat. The last one was a bit interesting as well. So that's one of the experiments where we used different ABR algorithms, so BOLA, low latency, throughput, and others. And we looked at the same MOS scores of in the background, we did try different technologies and different delay jitter values. And we looked at the upload and download ratios for them. So that kind of tells you that if a particular streaming service is using a particular algorithm, and if you introduce the technology, what happens? And is it the service, which service gets most benefit, which services don't? So it's giving us insights that we previously didn't think of. I think, yeah, that's where we are. I think we feel that it's a good time to revisit the application QoE and QoS relationship because we are all short of money. So having targeted network investment so we can improve customer service is great. And one way we can do is by understanding the QoE and QoS relationship. There is also another angle, which is where this is also an opportunity for the application developers and for the network operators to work together as well. I think in the previous presentation, someone mentioned about quality of demand. There is also work in standardization bodies like Cable Labs. We're looking at quality by design as well. So where we are using APIs to exchange information from application QA perspective, from a network perspective, and also providing hooks into the network where you can change certain things in the technology to improve this. So that's just a peek of what we are doing in the lab, how we are changing things. We'll be curious to see if someone's already done this or doing this. If there's any learnings, please do get in touch.
All right. Thank you very much,
Bjorn, I
Mulur.
pass it back to you. Yeah.
I have a question actually. You mentioned that you learned learned some new things about the upload versus download ratio for different streaming uh, what's the word? Codecs and stuff like that.
Yes.
Can you elaborate on that a little bit? Because I didn't fully get sort of what you were getting at there from the talk.
Yeah, I think it goes back to the question, right? Yeah, we had a question where in some of our networks where we had seen an upload increase. As we plan for capacity, we are very aware. But sometimes you would get these peaks in the network where you would see increased uploads. So there was a question of where is this coming from? So we thought instead of we were looking at the data, but we thought we'll run some experiments in to see how different streaming categories. If you carefully looked at the graph, there were two things called low latency and ultra low latency, where your segment sizes are a bit smaller or bigger, and then that makes a difference in how your upload and download works. And also, if you have higher latency, we've seen that there are some increased upload to download ratios. So there are some insights into why we see those peaks.
Understood. Right. Thank you very much. And with that, I think we will move to a break. So we'll do a almost 15-minute break and get started again at 17:20 Central European Time. And I'll bring up the agenda so that you know what's coming up. Hello, James. We are on a break now for a little while. And we'll start up again in about 10 minutes, just so you know.
Thanks.
All right. We are coming up on the end of the break. And so let me introduce our next speaker. James Carroll is Senior Director of Strategic Initiatives at Ookla, and he will be talking about internet observability at a global scale. So I will stop sharing, and James, as soon as you're ready, please take the stage.
Perfect, thank you. Hopefully the share is now working.
It is, yes.
Excellent. Thanks very much for the introduction. And for those who don't have familiarity with Ookla, Ookla is the company behind Speed Test, Ekahau, Down Detector, Root Metrics. And I think what you'll find each of these brands has, or each of these products has in common, is that we try to measure internet connectivity from consumer perspective. And I think, look, in a 3-day event like this with multiple companies and multiple people presenting, there are obviously numerous perspectives on what is the appropriate and the best way to measure anything. Everybody has their measuring tape. We all have certain different vantage points of the internet that we can view. And in reality, I'm not here to say the vantage point that we have is necessarily superior or better than any other, but each has got their own unique characteristics and views. And what we have, which is slightly unrivaled in the world, is that we have a global cross-network view. We are not isolated in one country, one carrier, one technology type, anything like that. On the fact that we have a consumer service and a consumer application, and we gather our information from consumer devices, we get this unique perspective that gives a global observability of internet fabric that is occurring. And there are limitations that come with having the place on the internet that we have in order to view this, but there are also great advantages in that we are a trusted third-party source of information for looking at global connectivity. And that has been the case for roughly 15 years. Now, it's a little bit difficult when you're at a webinar which is focused on latency and you are here from the company that has owns speed test. I think we're all aware that throughput testing, while it has its place, is certainly not as relevant now to internet connectivity as it was a number of years ago. I can even see in the chat prior to me joining, there's certainly some questions on how you can market latency as opposed to carriers going full out looking at throughput and throughput metrics. But nonetheless, there is a situation where when we are running throughput tests, we are also doing latency tests and we are also surfacing this. So for me today, with not much time to talk, I'd like to sort of just, in a very broad sense, talk about what it is Zookla do, how we do it, and maybe a small view at some data. I think with the time we've got, it's probably a little challenging to get through all of that. But in terms of numbers, we have got, roughly speaking, what we call 15 million consumer-initiated throughput tests that occur on a daily basis. That number is important, but it isn't necessarily hugely important for this conversation. What is, for everything I'm going to talk about hereafter, is the dedicated speed test server network that we have. And we are very lucky to have a huge amount of partners around the world in terms of ISPs, academic institutes, and government departments, interested parties who host speed test servers on our behalf. Or in conjunction with us. And these are the endpoints that we are mostly testing to. This is relevant for the fact that, largely speaking, where we would see these speed test throughput tests in being a very good last mile quality of service indicator. I would not go so far as to say that these are quality of experience indicator. They're very much quality of service indicator. So we are looking at a lot of the information that we are collecting from what you would traditionally associate with our company is latency information, which is going to those servers, which are generally at a geographic and a network topology point that is quite close to the person that is running the test. But given the fact that we all are aware that latency and latency information is considerably more important now and going forward, we have taken into now running latency checks in the background to other endpoints. So if you have installed speed test on your device, and if you have allowed us to collect these metrics in the background, we're also checking latency on an ongoing basis periodically throughout the day to interesting points of the internet. So be that gaming servers, video conferencing servers, and internet exchange points. So again, we're trying to take that view of, yes, from the consumer initiated tests where people do it, we will get extensive latency information to our own server network, but bridging that out from end consumer devices to interesting points in the internet is also what we're doing. And the numbers for what we are calling data quality of experience data set, the numbers for that quality of experience data set are ranking into the billions on a daily basis now, over and above the initial testing to our own server network. So aside from how everybody in a global sense measures and views and considers and understands latency and internet connectivity, even within our own one small little corner of this and one company, we are also involved here now in multiple manners of which we are measuring latency to different specific endpoints. Bjorn, sorry, I can see that there are questions coming in the chat, or there are comments coming in the chat. Do you want me to answer these as we go, or will we take it at the end?
I think probably at the end is better, just in the interest of time.
No problem. Sorry, it's just seeing it going. Thought I'd ask. So what is measured and what is surfaced? I think when we look at the chat questions around selling latency to people, or selling's the wrong term, informing consumers and end users about latency, we took the decision a few years ago to make the latency information that's surfaced in our application much more visible and much more evident, with a mild goal towards consumer education. Now, I will say it's incredibly difficult to win over the battle that in reality we have had multiple generations of marketing departments in carriers and companies moving towards saying more megabytes good, less megabytes bad. And when you look at the billions of marketing dollars and advertising that has been spent to push that message home, it's very difficult to then work on informing a mass audience about what ultimately is a KPI that is slightly beyond the majority of people's actual understanding. Nonetheless, right now in the application, when you run a test, we'll surface the latency information that was done not under load at the start of a test, and then we surface on an ongoing basis. We're taking latency to that same server while the test is under load. So I suppose we have got this loaded latency metric, which is visualized and then stored in the post-test visualization, which is what I'm showing there. Now, also, while somebody takes a test to any of these servers, we also have these other latency measurements, which right now we are not necessarily surfacing, and I'll get into a minute in our plans to bring more of these into the public domain in the future, but latency measurements to gaming servers, video conferencing servers, streaming servers, and also, most interestingly, some page load time information as well, which, while not strictly latency, is also much more applicable to modern internet connectivity than a full throughput test. The great advantage, or one of the advantages we as a company will always have, is that we have data. We have data, it's ongoing since I've been talking. We have had millions of points of data to come in. But I suppose what's interesting to look at is, this isn't a random bunch of countries, the majority of them are OECD related countries, and I didn't necessarily know what I could or couldn't show, but it is just to show that even the discrepancy amongst what we have got as our test endpoint. So I'm putting up here is 3 different figures that we have for these countries. We have latency in the first instance. That is when somebody is running a speed test, the latency to the server that they are running that throughput test against. That server more than likely is going to be quite close to them on a network basis. And these are the median scores for these markets on mobile connectivity. Then we have multi-server latency. Every time somebody tries to run a test, they get given a list of 5 servers to check against. The closest 5 to them. So this is the median across of those 5, bearing in mind that they will also be quite close to them. And then the last metric that's here is latency from those same devices at those same times to gaming servers, which, as we all know, gaming servers are not necessarily hosted in country. You will have quite a lot that are hosted outside the country. People are trying to check them. And again, what we see here is obviously a huge spike in latency. But what you see is the interesting aspect that countries that might have a lack of interconnectivity, submarine cables, hyperscalers active within those markets themselves have got significantly larger latency than they have in country, where the in country latency numbers might look quite acceptable. Then, when we're talking about latency to services that they are utilizing, it's very different. I only bring up this example to say that, like I spoke at the start, that we are very lucky to have the observability point that we have. But again, everything must be taken in context and understanding what it is that you're trying to measure and from what point and to what end and to what goal. So just presenting these outside of the emphasis of where they came from and how we did it doesn't actually assist anybody. So some people may have familiarity with the fact that Ookla for years has published what we call the Speed Test Global Index. And Speed Test Global Index is an incredibly interesting and useful tool. It, on a monthly basis, has been benchmarking countries' throughput performance and publishing it. And when I say it's a useful and interesting tool, where this has been most interesting is that we have seen this tool I'll be fully honest. In the first instance, when we released a tool like this, we were looking at trying to just bring some of the information we had into the public domain in an interesting way. We didn't necessarily have huge, lofty goals for it. However, this took on a bit of a life of itself, and we saw that there were certain markets in the world where a driving interest to rise up the global index led to an exceptional increase in internet connectivity for citizens of certain countries. So it had a very positive and beneficial effect. However, we now get to a stage whereby we have got some countries which would have incredible throughput performance, but might not necessarily have good experience for the applications that people want to experience. So in reality, poor latency performance to services. So next year, and it's where I said earlier on, some of the metrics that we are collecting in regards to latency to gaming servers and latency to video servers. Next year, we are going to, through the global index, pivot it towards being an index which is also looking at latency and readiness and other items. So that is our goal for next year in terms of being able to showcase, I guess, that latency is probably the preeminent metric that is required for measuring internet capability going forward. And lastly, again, I just wanted to show, and I could spend all day pulling out examples of how we have how latency matters and how we utilize it. But it was just I'm based in Dublin in Ireland, and we had a storm by international standards, a mild storm by Irish standards, quite a violent windy storm over the weekend. And it was just the interesting piece that over the weekend, unsurprisingly, as numerous cell sites came down across the country due to either trees coming down on them, power outages, or other problems, we saw the networks themselves actually stayed up. The resilience of the networks these days is quite incredible. But the obvious real life example of what occurred is there were genuine latency spikes which occurred across those networks until recovery was put into place. So it's just an example of the data that we're collecting on an ongoing basis and how it can have a real world application and utilization to be shown what is occurring for end consumers at any point. And with that, I'm happy to take any questions.
All right. Thank you very much, James. Let me see. There's been a lot of chat in the chat here. I'm not sure I'm able to dig out the questions from all the banter here. Let me see. Yes, Dave is maybe more of a comment actually, but he's saying I keep hoping speed test would aggregate their responsiveness metric by ISP and publish. Comments.
Comments. I mean, there is, sorry, it's a comment I'll pass forward to the analyst team, for sure. I mean, there is a endless set of things that could be published and brought into the public domain. So yeah, I'm happy to pass that comment forward.
All right, and Chris is asking how do Ookla plan to evolve your latency responsiveness measurements going forward?
It's an interesting question. I think for me, and again, I shouldn't necessarily speak for the product organization at this point. What we have right now is an unrivaled observability framework. We have got 15,000 servers that are spread across the world. We have millions of installed users. We also have actually tens of millions of CPE embedded with the speed test capabilities. When we talk about evolving it, in the first instance, I'd like to get full utility, or we'd like to get full utility out of what we currently have, because I don't believe we have yet scratched the surface in understanding what can be done with, and one of the most notable things that there is a gap in what we are measuring and what we're publishing is latency information between those servers. So the server network itself is actually testing to itself, and not full throughput testing latency across the backbone of the internet. So being able to develop tools and being able to develop a view in terms of what is occurring at the core of the internet from some of the latency measurements, from some of the observability points that we have, would be certainly something that would be of great benefit, and something that we would like to do, that is always there on the medium term roadmap, but always kind of gets client requests tend to get in the way. So it's sort of my belief that there are not necessarily new test cadences, but new end-to-end points that we should start to look at and then visualize.
All right. Thank you very much. And I see now the questions are rolling in here, but we have to move to the next speaker. So if you have time to address those in chat, that would be very good.
No problem.
Thank you very much, James.
Thank you.
Our next speaker is Koen de Schepper. He's the research principal at Nokia Bell Labs, and we'll talk about understanding L4S for Wi-Fi. So Koen, please take the stage.
Okay, thank you. You can hear me and
I can hear you and see you.
My screen should be coming up. Is that the case
Yes.
for you? Yeah.
That is looking good.
Okay. So thanks again for the invitation and for the interesting webinar. The topics I'm going to talk today, there are two topics. If I can move my slide here. Yeah. Two topics that I want to talk today, so the time might be a bit too short, but since I'm the last one, I hope I can have a bit of slack time. If not, then I have to hurry a bit more. So the two questions here, can we adapt dual pi square to Wi-Fi MAC latency? There are, of course, a lot of discussions. How should you make a dual pi square concept mapping to Wi-Fi? I can give you some more information about that here. And then, of course, when we apply an AQM to a system, and especially Wi-Fi, not all latency is queuing latency, and we have some residual latency. And can we improve that? Without L4S, okay, it's hidden in queuing latencies when the Wi-Fi channel is busy. But if you remove the queuing latency, then of course it becomes interesting and useful to remove the MAC latency and trying to improve, find ways how we can further reduce the latency. Okay, so first question. We see typically a lot of latency still. Even in this case, we have a very good active queue management system for L4S. This is L4S traffic. We still see quite large undeterministic peak latencies, and I saw many presentations in the past also explaining this a bit. We see also still a lot of MAC jitter, Wi-Fi jitter, And then also a kind of a base latency, which is there always when you fully use the capacity of a Wi-Fi link. You will see have a minimum latency as well, which is typically related to the transmission opportunity, the transmit opportunity. Quickly giving an overview how Wi-Fi works for the ones that are not so familiar with it. Probably there are experts that know the detail, but first of all, this transmit opportunity is, you can compare it. I always compare it with a train arriving. You can load the train, packets are waiting on a platform. You try to fill the train as much as possible. If these transmit opportunities are limited in time, so like a train, it's limited in capacity as well. It depends a bit on your channel conditions, how many packets you can push in that train. You see this train has a better channel condition, you can put more packets in there. What you also see is that you have overhead where you can't store packets, but they take time, and that's quite substantial for Wi-Fi. Then when the train leaves, actually there is no planning for when the next train is going to come. That's a completely random kind of thing, which depends typically on two things: that how busy the channel is by others, and also a bit depending on a random backup counter. And that random backup counter, if it's small, then also not many others can gain in or use the channel. If that is bigger, whenever somebody else gives more others to give opportunities to send, and you're actually waiting a long time, you have to let a lot of other people or other trains use the channel. So causing at the end quite big latencies. So these variations in throughput are the jitter, and this transmit opportunity is some kind of, the typically for best effort 2.5 milliseconds is kind of standardized or followed, but there are a lot of deviations to that. So to look at this, we did some tests. So really to look at the MAC latency, just to give you an idea, how does it work? We have two devices, two laptops in this case, which send full buffer UDP packets to access points, and we can easily with Wireshark look at the spectrum, capture the packets, the Wi-Fi frames. And then with a tool that we made, we can analyze a bit what's going on. So these are just two upstream flows, which tries to keep the buffer full and always try to compete for this channel based on this mechanism that was explained. And here you see a few things. This is a transmit opportunity time. So here we see for every frame that we saw how long it is sending data. This is the inter-transmit opportunity. So that's actually the time between trains arriving and can be filled and leaving again. So this is causing latency. It's in milliseconds as well. Also the transmit opportunity in microseconds in this case. So typically it was 2.5, I said. So the real data that can be sent, here you see a PDF of it. A CDF of it is 2.250 milliseconds. So there is, let's say, 200 to 300 overheads in that case. And then here you see also the distribution of this inter-peaks uptime. You see for best effort, the 2.5 millisecond steps that trains, you have to wait that trains are busy, that you can step in and a train arrives. But there is quite a big, long tail at the end. So in general, when with this access category best effort, 2.5 milliseconds, since we have two stations, you typically have to wait two transmissions on average. So the average latency is about 5 milliseconds, and the peak latencies are here 100 milliseconds. even not showing up in the 99.99 percentile. So a 99.99 percentile is not necessary over a period of 10 seconds, the biggest latencies you can experience. And if we would run or show different results, there might be results which can go to many hundreds of milliseconds, because you see this tail is broken here, but it goes smoothly, continuing much further. So knowing this, how can we map then dual pi square, which is the active queue management for Alvarez in RFC 9332, where it's mentioned, of course, you have to use 1 millisecond sojourn time. If you know that your train only, that packets needs to wait at least 2.5 milliseconds up to a few hundreds of milliseconds, having a sojourn time measurement, checking how long your packets has to wait on the platform before they can enter the train, they all will get marked because they all exceed 1 millisecond. So that's not a good strategy, because all your packets will get marked. And your Alvarez throughput will drastically drop, and you only have a few marked packets in every train. And if you can't fill the train, of course, your throughput collapses completely. So not a good strategy. Let's try another one. Another one is, okay, if a train arrives and we have packets on the platform, we can load the train and the train is not full. Why do we need to mark, right? When do we mark? When the train arrives, but the train is full and still packets have to stay on the platform at that time. It's a good idea to mark them all. We know how big this train is typically in Wi-Fi. We have a transmit opportunity time limit, 2.5 milliseconds. We know the channel encoding up front. Based on previous transmissions, it's calculated, estimated, based on some heuristics. So we know upfront how many packets we can put in there. So we also know, even after having been filling the train, how many are left, and we just mark them all. And that seems to be a more sensible strategy, because here the target is to get the trains as full as possible. So not losing transmission opportunities, and trying to minimize the packets that have to wait on the platform for the next train. Looking at the results, this is pretty nice, I would say. Here we see comparison between classic one, which doesn't have an AQM at all. And you see here the latency goes quite high. The throughput, you see here when the buffer is big, you see those dips, they don't harm. Your throughput in orange here is very high. But when the queuing latency is a bit lower, you miss some throughput. And if you see here the orange one, when the latency is low, when the flow is still starting, you see also that the throughput in the orange one is low. That immediately explains also, if you keep those trains and don't have a lot of people on the platform waiting for several trains, if you only try to keep one train full, you lose some throughput. So this is just trains which are not fully loaded, because there is no deterministic arrival of those trains, and you cannot always fill them. But actually, we have a reduction of factor of 20 in latency, and we only have, let's say, a quarter of a throughput reduction, which is not so high price to pay for having well, 20 times reduction in latency, I would say. Then going further, how do we handle the coupling? And also the dual pi square. You will see here, you recognize the classifier, the two queues, pi square, which drops packets in the classic queue based on the classic latency, and also marks packets with the coupling for Alvarez. And then something different, let's say, it's not a weighted round robin, it's this weighted aggregator. And how does that work? So what is that aggregator doing when a train arrives? It's empty and it needs to be filled. Well, it gives priority to all the alpha res packets. It puts them all in the train. And if there is space left, it's being topped up with classic packets. That sounds okay, maybe not it's not a full story, at least up to this point. The 90% is also a limit for the alpha res packets. So if the train is 90% full, the priority for alpha res stops and you can load classic packets. If there are classic packets, if there are no classic packets or not enough, we can still fill the train with alpha res traffics. And then when there are, after the train leaves, you check how many packets are still in alpha res. You mark those if they are still there. Otherwise, you don't have to mark anything. Of course, giving priority to alpha res creates a queue for alpha res for classic traffic, and then the pi square AQM comes into place. It drops packets, but it also marks packets. So the next train arriving, depending on the queue here, the alpha res traffic, the alpha res packets are being marked with this double probability compared to the squared probability for the classic one. And you know the story, it gives the same throughput for both. And then alpha res flows back off, so making a fair filling of these trains. So showing alpha res is very implementable when you do it in the right way. Alpha res is also important for Wi-Fi because there's a lot to gain. Easily factor of 10 and more lower latencies, 2 times, at a cost of no more than 2 times rate reduction, 25% maybe. Since we speak about huge capacities in the future anyway, it's not a big price. But also, of course, Wi-Fi is very important for alpha res because Wi-Fi is often the biggest source of latency. We need to tackle that definitely. And it's a proven technology. Like I said, we've implemented alpha res in Wi-Fi Nokia beacons for a long time on many existing chipsets. So that's okay. This is a bit the story. The first topic, how can we adapt dual pi square on a specific network technology? On the other hand, of course, we adapt and we try to make the best of the network technology. On the other hand, we also have a mechanism that kind of allows now further optimization. One of the optimizations would be to have more deterministic trains, not having this very varying trains scheme. So many opportunities. And the good thing is this AQM implementation automatically adapts when we also make this MAC layer better. So let's have a look. How can we improve? And many presentations already talked about WMM. Maybe a bit of a spoiler here. It looks at first sight a big improvement, but looking deeper at it, it's not going to help us. It's even part of the problem sometimes, I would say. So, but there are other alternatives, and it's a good time to revisit WMM or the concept from its own, because there are clearly low-hanging fruit if we optimize this that even performs better than any combination, as you will see. So we will be trying these different settings in the same setup, only 2 stations sending with these different access categories, or a new setting. And to give you a quick explanation, this is how long you have to wait after an idle, after busy channel use, how many slots of 9 microseconds. This is the minimum random number, the maximum random number you have to use to wait and to count back. And then this is the time that you're allowed to send. So this is transmit opportunity. So you see the different numbers. Video just waits less long, uses smaller random numbers, transmits longer. Voice even halves those values of waiting between the minimum and maximum random numbers. and also halves the time it uses the spectrum. So we expect them to be more fair. One proposal here is, well, we don't want to differentiate anymore because there are also access points have to wait only one slot, fixed number. If we just ignore this and try to wait at the minimum time and then use a large enough value for random numbers, and in this case, no exponential backoff, and try to minimize the sending time, it sounds very simple. This is less aggressive than video and voice, definitely, and it's probably fair against best effort. So let's try to see what the results are here when we test with those new EDCA parameters. So just a quick recap before best effort was the first line. We already saw that 2.5 milliseconds, 5 milliseconds average latency, and 100 milliseconds peak latency in this 10-second test. You know that. Looking at video, it seems to be a good improvement, and that's what people typically see also. We have 3 milliseconds, so the average latency increases a little bit with video, but the peak latency is drastically reduced, well, a third. You also see it at the CDF. And another maybe important number is this link utilization. The airtime, which is really used, is 90%, similar like the best effort one. It's also 90%. The video gives the same airtime when two stations are competing, let's say. And two stations, that means your access point and your VR glasses potentially, because if you have some bidirectional traffic or in a video conference and you're trying to use all the capacity in the link, you're having these two competing already with each other, and you get this level of contention. If you have two devices, there might be 4 parties that are competing, so you always have to think in both directions potentially. So using voice, we halved all the parameters. So again, especially the transmit opportunity is halved as well. Also, the latency, the peak latency is halved, and the average latency, so more or less like expected. So it seems also to be a good improvement. Looking at this new and competing with itself, again, we only sent 1 millisecond, so we can even further reduce it with an average latency of only 2 milliseconds and a peak of 10 milliseconds. So it's up to now the best one that you can use, actually. It's better. But the interesting part is when you start combining all of these. So we showed here the throughput and the 99 percentile in this case. You see the throughput, best effort, video, voice, and this new one competing with the same 4 and all the combinations. We saw this one, so we have a rate about 100 megabits with 20 milliseconds, 99 percentile. The longer tail is not shown here, but becomes too big in other cases. We saw before the video, and you see the latency of video, the 99 percentile is not much better than best effort. The voice competing with voice is, okay, significant lower latency. Throughput also is a little bit less than this one. And if you look at this one with a bit more throughput or a bit lower throughput, we can even improve it below the voice. That's what we saw. But the interesting part is if these compete with the others. So with best effort, video competing with best effort gets a much higher throughput at the cost also of a much lower best effort throughput. Also, it get an improved latency, but also again at the cost of a much higher latency of 99 percentile. If you look at video competing with video, this latency is not yet, is almost lost. So you're only getting lower latency at a much higher cost of your best effort. And actually, the latency that you gain with video and with voice, it's similar with voice. It's even pushing it further down, both getting a lower throughput than video and making best effort even going lower. If you compare this with this new, you get, if both use this, you get the same low latency for both as if you would get for voice, and you don't cause any bigger latencies or lower throughputs to the others. So what else can we see here? What if our new is competing with best effort? We see we get the same rate. Okay, we get a lower latency, which is, unfortunately, it's not better to use best effort. So even the best effort one should better use this one. It would get, okay, a little bit less throughput, but it wouldn't get its own bigger latency. And we would, when we use and we compete against ourselves, also get a lower latency in total. So a win-win, but it's not as bad as using video or voice. Also competing with video and voice, we see that our new still doesn't have that much damage compared to best effort getting damage. But the throughput is, of course, also reduced, but also not that much as with best effort. So doing the same for more stations will show that video and voice are further deteriorating themselves because they create more harm against themselves and definitely to the lower priorities. While doing this with this, you always see it's better. So there is kind of a better solution here, low hanging fruit already. So is the right conclusion that we should forget WMM and even avoid using these access categories, video and voice, because they don't seem to be the solution. They seem to be more part of the problem. And maybe it's time to define a better MAC, rethinking the MAC with the lowest latency as objective instead of trying to always achieve the highest throughput. With that, I'll give the word back to you, Bjorn.
All right. Thank you very much, Koen. Stuart requested to give a comment, so I think he'll ask a question live.
Thank you, Bjorn. It's not a question for Koen. It's an observation. I've been watching the chat. I'm seeing people saying that prioritization is the only way to lower latency. And that's just wrong. People have been thinking that for 30 years, and it hasn't worked. I see people in the chat saying that latency is a zero-sum game. And that really disappoints me. We've just had a 3-day workshop talking about latency. And this is the third of these Domos workshops talking about latency. And somehow we've failed to get the message across to people that the big difference is that bandwidth is a zero-sum game. If you give more bandwidth to one flow, you have to take it away from something else. Latency is not a zero-sum game. If a flow is sending 10 megabits over a 10 megabit bottleneck, well, that's not how networks work. The flow will try to explore to see if it can send a bit more. It might send 10.1 megabits. But that's not getting more throughput at the receiver. If the bottleneck's 10 megabits, the receiver is still getting 10 megabits. That flow is not getting more than 10 megabits. But the extra 0.1 means that a queue is starting to build up. And the key insight of ECN and classic ECN and modern ECN with L4S is that latency management is a partnership between the senders and the network. And if the network tells the sender, look, you're fine with the 10 megabits, but you're building up a queue. So you should pause a little bit, let the queue drain. You can still get the same throughput, but you could do it with a shorter queue. And giving the flows the information so that they can work themselves to avoid building up a queue is not hurting any other flow. It's not a zero-sum game, and that is the great insight. And maybe next time we need to work on some presentations explaining how latency is not a zero-sum game. We can give low latency for all traffic. It's not something where we have to prioritize that some privileged traffic gets it and some other traffic doesn't get it.
All right. Thank you very
Yes,
much, Stuart. I want to maybe if I can expand on that a little bit. I think so. I see Sebastian saying that scheduling is a zero-sum game, and I think that's true if you're thinking if you're not thinking of it as an iterated game, right? Because it's an iterated scheduling effort over a period of time, and if you can get feedback to the clients, then you can get them to cooperate, and you sort of avoid that first scheduling problem. But yeah, I know this is a difficult and complicated conversation, so let's move to questions for Koen here. Matt is asking, how well does your results compare with intrinsic limits based on a zero sum or work conserving models?
Related to work conserving, it's work conserving, right? It's the only thing is the overhead that you have to pay a little bit. So the reduction in throughput is here mainly the fixed overhead, and there are many opportunities to improve. Possibly, I'm not a physical layer, but looking into the physical layers to optimize for lower latency, to remove the overhead of the packet scheduling, especially in new spectrums, instead of reusing the same mechanism and being compatible to something which is never going to be used anymore in that new spectrum, is a bit of a, well, I'm not the expert, but there are many opportunities to improve here. And instead of making things more complex, I think it's rethinking the foundation and like Stuart also said, it's not always this zero sum game. Yeah, I don't know whether I've answered the question, but I don't completely understand because okay, there is work conserving is one aspect. It's time conserving, but okay, you have more overhead. So at that point, it's maybe less work conserving. But yeah, the optimal transmission is that one station is continuously sending and there is no overhead in that case. But that's also not a solution, right?
All right. Thank you very much. And that actually concludes our list of talks and speakers for this event. So thank you. I want to thank all of the speakers who have presented today and the previous 2 days. You are what makes this event worth showing up for. So thank you very much for taking the time to share your knowledge with us. I also want to take an opportunity to request some feedback from people. So we have experimented a little bit with different formats. For the first event, we had panel discussions. For the second event, we had longer talks, and the whole like each day we had 3 days, and each day was about 4 hours. So that was a bit intense, which is why we made the presentation slightly shorter this time and made slightly fewer of them. If you have ideas, thoughts, feedback on the format or on which speakers we should have, because even though I'm very happy with the lineup that we have, we don't know everyone working in this space around the world. So if you know someone who should be on the list for the next event, please shoot us an email, or if you think you should be on the event, likewise, just let us know. And I want to end with a small, well, sort of plea, I guess. To I know there are some ISPs or people representing ISPs in the audience, and just to wrap up the event, I want to. I want to reach out. I hope that we can have more ISPs that are not like this ISP. It turns away from the fixing the hard stability issues to reach for the very tempting higher bandwidth numbers, capacity numbers. So I am hoping ISPs will not choose to do this and will do this instead. That is my closing remarks for the event, and I hope it sort of sums up the very high level message of the speakers that we've had on. So with that, thank you very much to everyone who's shown up and participated in the chat and spread the word on social media and everywhere else. We really appreciate all the attention that this is getting and all the work that the speakers and people in the audience as well are doing to improve latency in the internet. So thank you very much, and I hope to see everyone next year.